Welcome to the course entitled Symmetry, Stereochemistry and Applications. In the previous lecture, we have been discussing about various organic reactions, and in those lectures, we have talked about the different reducing agents and their effects on various carbonyl compounds. So, in today's lecture, we will start with the discussion on the oxidizing agents in organic chemistry. Some of you may have studied in your 10 plus 2 different oxidizing agents in organic chemistry, and those are chromic acid, pyridinium chlorochromate, or in abbreviation written as PCC, or potassium permanganate, which are routinely used in organic synthesis for oxidizing various compounds. PCC is generally considered as a mild oxidizing agent, and it oxidizes 1 degree alcohol or primary alcohol to aldehyde. Jones reagent, which is chromic acid, is a harsher oxidizing agent, and it oxidizes 1 degree alcohol to a carboxylic acid. This Jones reagent can be easily prepared in the lab using potassium dichromate and concentrated sulfuric acid. So what we do is we choose the oxidant based on the desired carbonyl functional group that we want upon oxidation. So just like the previous lecture where we talked about the effect of different reducing agent on various organocarbonyl compounds, here I am tabulating the effects of these two oxidizing agents on various alcohols and the corresponding products. We generally don't try to oxidize 3 degree alcohols, we only try to oxidize methanol 1 degree alcohol or 2 degree alcohol. So if you use PCC, pyridinium chlorochromate, it can oxidize methanol to formaldehyde, 1 degree alcohol to any other higher aldehyde, 2 degree alcohol to a ketone, and it does not have any effect on a 3 degree alcohol. You see that this oxidation using PCC is restricted up to aldehyde and ketone, and it does not oxidize the alcohol to the highest oxidation state, that is carboxylic acid. If you want to do that, if you want to oxidize a compound to its carboxylic acid, then we should use this chromic acid or Jones reagent, which oxidizes methanol to formic acid, 1 degree alcohol to a corresponding carboxylic acid, and of course a 2 degree alcohol can only be oxidized up to ketone and not to a carboxylic acid. So depending on what kind of product you are trying to form, we should choose appropriate oxidizing agent and the reaction conditions. So let us see a few examples here. So in this particular first example, this alcohol is a 1 degree alcohol, and when you are using PCC in presence of dichloromethane at room temperature, we are getting an aldehyde prepared. When we have a 2 degree alcohol, which is shown here as a cyclic alcohol, a cyclohexanol derivative, and in presence of acetone as a solvent at about room temperature, the reaction yields a ketone. And on the other hand, if you just use 1 degree alcohol and use potassium permanganate in alkaline medium and heat it, that is aqueous KMnO4 heated with sodium hydroxide solution, this 1 degree alcohol is then converted to the corresponding carboxylic acid. So depending on what kind of reagent you are choosing, the product is different. In the first case, we have seen the formation of aldehyde. Second case, it has formed the ketone. And in the third case, when we have changed the reagent from chromic acid to a potassium permanganate, then we are getting a carboxylic acid as the product. Let us see how this reaction proceeds, how the oxidation reaction happens using the chromic acid oxidizing agent. So when you take an alcohol which has lone pair of electrons, so that lone pair of electron attacks the chromium center and the carbon oxygen bond opens up as is shown here, and it forms a chromate ester, and the reaction is happening in acidic medium. So immediately the chromium oxygen bond opens and OH bond is formed. So you have two OH groups and one anionic O minus in the molecule. So this compound then further rearranges by the formation of a fresh carbon oxygen double bond and elimination of this OH as water molecule, and this forms this compound which is called the chromate ester. This chromate ester then further reacts with the water molecule, which takes up the proton from the carbon adjacent to the oxygen, and double bond forms with the electrons that are present in the carbon-hydrogen bond with the oxygen, and oxygen-chromium bond gets broken. As a result, H3O plus, that is the acid, is released and a ketone is formed, along with the reduced form of the chromium reagent. If you see here, the oxidation state of chromium here is 6, and in this case the oxidation state of chromium is 4. So there is a reduction of the chromium reagent, whereas the substrate is oxidized. So hope this reaction mechanism is clear to you. Let us try to then see other different organic reagents that are used in various organic reactions. So let us start discussing about organometallic compounds. As you can understand, this course is a very basic course, and we will just discuss a few organometallic reagents and their reactions and the products that they form, and the reaction mechanisms will not be discussed at this point. These organometallic compounds are those compounds which contain a carbon-metal bond. This bond, carbon-metal bond, ranges from ionic to covalent. So some of the carbon-metal bond may be ionic in nature, some may be purely covalent in nature, and some may be intermediate, that is between ionic and covalent in nature. So examples of carbon metal bonds which are ionic are carbon sodium bond, carbon potassium bond, whereas the primarily covalent bonds are carbon lead, carbon tin, and carbon mercury compounds. The intermediate carbon metal bonds are very important. Those are carbon magnesium and carbon lithium, which forms a character which has similarity between both are ionic and covalent bonds. And the reactivity increases with ionic character of carbon metal bond. So when we try to use these reagents which have carbon metal bond, these reagents are always very highly moisture sensitive. That means they are hygroscopic in nature. So their reactions should be done in a very dry condition and without any trace of moisture. So for those type of reactions, we use two different types of solvents, both are ethers. One is diethyl ether and the other one is tetrahydrofuran. Some of you may recall that this compound is called furan, which is then hydrogenated to give you the tetrahydrofuran. So normally what we do is we take these solvents and we dry those solvents on metallic sodium. As some of you may be aware that metallic sodium is highly reactive towards water. These solvents are taken in a round bottom flask with sodium, and then the mixture is boiled for a long period of time with a condenser on top of it, and then after a few hours of boiling with sodium, these solvents are then distilled and collected round bottom flask and used for further reaction. So this drying of solvent is very important in this particular case. So when you use this dry solvent, the dry diethyl ether with lithium at minus 10 degrees centigrade, and alkyl halide gets converted to the corresponding alkyl lithium compound. Here it is butyl lithium compound. Remember that this butyl lithium compound is highly moisture sensitive, therefore the reaction has to be done under nitrogen atmosphere in a very dry condition. The reactivity of halide is as usual that iodides are more reactive than bromide and bromides are more reactive than chloride, and the alkyl fluorides are not generally used because the carbon fluorine bond is very strong and it cannot be broken so easily at minus 10 degrees centigrade. One of the most important organometallic reagent is Grignard reagent, which you must have heard about. So a Grignard reagent can be formed if you treat an alkyl halide with metallic magnesium in dry ether. It forms this magnesium bromide, which is here the butyl magnesium bromide, called the Grignard reagent. This reagent is also highly moisture sensitive, so we should use always the dry solvent to make this compound. So even with phenyl bromide or bromobenzene, you can generate phenyl magnesium bromide using the same reaction procedure. Again, the reactivity of these halides are same for organolithium compounds, that is Ri is most reactive, and then Rbr, and then RCl. So these organometallic reagents can act as nucleophiles towards polarized carbonyl groups, that means C double bond O group, which is del plus and del minus, that is the polarized carbonyl group. They act as very strong Lewis bases. So they react with acidic protons. So they react with alcohol, they react with acid, they react with acetylene, where the acetylenic proton is acidic. This basicity requires a very high dry condition, so we always avoid contamination of water. The reason for basicity is the carbanion-like behavior. R MgX can be considered as R minus MgX plus kind of a polarized compound, where the R is like a carbanion. Therefore, it behaves as a strong base. So this is a strong enough base to deprotonate terminal alkyne, which I have already indicated, which means if you have a C triple bond CH group, it can deprotonate that hydrogen from this compound. If there is no acidic proton, it can do nucleophilic substitution reaction as well. So in the next slide, let us see some of the representative Brignard reactions. So when you use a Grignard reagent with a cyclic ether like this, which reacts with the alkyl magnesium bromide, and upon hydrolysis it forms a 1 degree alcohol. This cyclic ether, which is substituted here, reacts in the same manner to generate a 2-degree alcohol. So Grignard reagent nucleophilically opens these epoxides and generally attacks less substituted carbon, which is here, and view this reaction as a carbon ion attacking in the form of SN2 reaction. This negatively charged or negatively polarized carbon attacks the less hindered site, and simultaneously the carbon oxygen bond opens up to give you a reaction intermediate, which upon hydrolysis gives you the product 2-degree alcohol. So when you use these Brignard reagents with different carbonyls, you get different types of products. Grignard reagents react with a variety of carbonyl compounds. If you treat formaldehyde with a Grignard reagent, you will get a 1-degree alcohol. Any other aldehyde will lead to 2-degree alcohols. Ketones will form a 3-degree alcohol, and esters also will form 3-degree alcohol. So, attack of Grignard reagent generates alkoxides and protonated to get the OH substituted in the compound. So let us see a couple of such examples. In case of phenyl magnesium bromide treated with formaldehyde generates a 1-degree alcohol, which is benzyl alcohol. This phenyl magnesium bromide, when it is treated with the acetaldehyde, that is 2-carbon aldehyde, it generates a 2-degree alcohol. Phenyl magnesium bromide, when treated with a ketone, generates a 3-degree alcohol. So depending on the substrate on which the same Grignard reagent is treated, you generate different alcohols of different degree. When the same phenyl magnesium bromide is treated with an ester, this reaction happens in 2 steps. It reacts 2 times with esters to form a 3-degree alcohol, which contains the alkyl or aryl groups that are there in the Grignard reagent. So with 1 equivalent of the ester, 2 equivalents of Grignard reagent reacts to form a 3-degree alcohol, right? Now let us see some of the reactions of organolithium compounds. Organolithium reagents react similarly to Grignard reagents. They are also strong bases and have same limitations, like they are highly moisture sensitive. Therefore, one has to maintain the moisture-free and oxygen-free conditions, and therefore we should use these reagents under nitrogen atmosphere only. These reagents are more reactive than Grignard reagents. So routine synthesis, we always prefer to use Grignard reagents which are less reactive, and these alkynides like the triple bonded anions react in the same manner with aldehydes and ketones. So when you try to understand some of these reactions, first we need to make the corresponding lithium dialkyl cuprate reagent. So when you treat methyl bromide with 2 equivalents of lithium, you get the methyl lithium, and then if you treat methyl lithium with copper iodide, you get dimethyl lithium cuprate. So this dimethyl lithium cuprate is the corresponding organometallic compound that we use to convert a number of different organic compounds. So here the example is that iodocyclohexane is converted to methyl cyclohexane using dimethyl lithium cuprate in dry ether medium, or a bromo compound is converted to this methyl compound, keeping this double bond unaltered in the reaction medium. So this reaction is very useful in the formation of a new CC bond. Here, this carbon is now bonded to another carbon which is coming from your reagent which has a methyl group. So, there are many such reactions in which you will encounter these organic and organometallic reagents. I'd like to suggest that you please go through the textbook that are prescribed for this course and follow those reactions from the textbook. In the following lecture, in the coming next lecture, I will discuss about some of those reactions and give some examples. Thank you.